Good morning to all of you. This is Naren Sharma from Government First Grade College, Vartur. Continuing discussion on quantum mechanics part 2 of BSc Physics course, 6th semester, paper 8. So today's session number is 7. And in today's session, I'm going to discuss about linear harmonic oscillator. Basically, we are discussing about the applications of Schrodinger's equation. So today we shall try to understand what are the things that we are going to get when we apply Schrodinger's time independent equation to. So another physical example of one-dimensional linear harmonic oscillator. Now let us see the objectives. The objectives of this particular session, as I have already told, to apply Schrodinger's equation to one-dimensional linear harmonic oscillator. What is a linear harmonic oscillator? We should try to understand a little later. We want to apply Schrodinger's equation to a physical system called as one-dimensional linear harmonic oscillator. So after applying the Schrodinger's equation, we shall try to solve the equation, not completely, partially. And through this partial solution, through this partial method of finding out the solutions, we shall try to derive an expression for the energy eigenvalues of the linear harmonic oscillator. We successfully derived expressions for the energy eigenvalues of the particle, which is trapped in one-dimensional box as well as three-dimensional potential box in the previous sessions. We are doing the same here also, and we shall try to find out an expression for the energy eigenvalues of one-dimensional linear harmonic oscillator. And we will come to know that, so just like particle in a box, even our linear harmonic oscillator has discrete set of energy values, and those discrete set of energy values are actually given by energy eigenvalues. What is the expression for the energy eigenvalues? We shall try to derive. And also we shall try to write down the expression for the wave function of the oscillator. And using the word, we are trying to write down the expression for the wave function of the oscillator. It is because we are not going to derive the solutions completely, as it is not there in the syllabus. So we shall try to mention the wave function form for the linear harmonic oscillator. And once we know the mathematical form of the wave function of the oscillator, it is also possible to plot these wave function for certain cases, for certain energy levels, for certain quantum states, few quantum states. So this is what the objective of my discussion. So here we are applying Schrodinger's equation to a linear harmonic oscillator, and we are trying to solve the equation partially, and therefore we can obtain the expression for the energy eigenvalues. And also we shall write down the expression for the wave function of the oscillator, and we shall plot this wave function. So let us continue our discussion. So it is linear harmonic oscillator, one-dimensional case. Before we apply Schrodinger's equation to the linear harmonic oscillator, so we need to know certain things, few basic things as per classical physics. So classically, a linear harmonic oscillator is a one in which the restoring force F, which is acting on a particle of mass m, is linearly proportional to the particle displacement x from its equilibrium position. Suppose we have a particle, and if the particle is in the equilibrium state, so then if we try to push the particle or pull the particle in any one direction, either in the positive x direction or in the negative x direction, so the particle is acted upon by a force called restoring force, and so the manner in which the restoring force varies is such that the force is directly proportional to the displacement, and force is always directed opposite to the direction of the displacement. So therefore we can say F is proportional to minus k. I have not written that one. I have written the complete expression here. Once we remove the proportionality, we end up with a constant also. Anyhow, so a linear harmonic oscillator is a system in which the restoring force is directly proportional to the first power of the displacement from the mean position, and the linear force would be always acting in a direction opposite to the direction of the displacement. That's why we have a negative sign. So therefore, in the case of a linear harmonic oscillator, F, the restoring force, is proportional to minus x, where x is the displacement of the particle from the equilibrium position or the mean position. So therefore, we can write that particular expression as f is equal to minus kx. So where k is some constant. In the case of a spring, it is called a spring constant, whereas in the case of general linear harmonic oscillator, so this k is called some elastic constant. And basically this f is equal to minus kx is nothing but Hooke's law. Whatever the relation that we have written, this is what is called as Hooke's law. Hooke's law is a basic law in the case of elasticity, as we know. So therefore, even in the case of one-dimensional harmonic oscillator, it is possible to use the relation f is equal to minus kx called Hooke's law, where f is the restoring force, so acting on the particle on the oscillator, x is the displacement of the oscillator and the particle of the oscillator, and k is some constant, elastic constant, that force constant, whatever it is. Now it is possible to make use of Newton's second law of motion. So since we are discussing this whole linear harmonic oscillator classically, so it is always possible to use Newton's second law of motion. So therefore, according to Newton's second law of motion, we can write, so ma is equal to m into d square x divided by dt square. So the applied force is nothing but ma, mass into acceleration. And since the motion is along x-axis, one-dimensional, so therefore the displacement is denoted by x. So therefore acceleration in terms of displacement can be written as d square x divided by dt square. So therefore force is given by m into a, that is also equal to m into d square x divided by dt square. And we can write, so that is equal to minus kx, as the applied force is equal and opposite to the restoring force. So therefore, as per Newton's law, we get the relation m d square x divided by dt square must be equal to kx. And if you simplify this particular expression, so then we are going to end up with one differential equation. So equation 2, so it says that d square x divided by dt square plus k by m times x is equal to 0. So this is the equation 2, or this is the differential equation, so which is applicable for one-dimensional linear harmonic oscillator. Basically, this is a differential equation. Now, so in order to solve this equation 2, this is a differential equation. So therefore, it is possible to solve this differential equation. To solve, what we are doing is we are doing certain simplification. So in the previous expression, we had something like constant k by m for a given system of linear harmonic oscillator. So therefore, this k by m chosen to be something else, something like a constant, and we write it as omega square. And therefore, this omega is what we call it as the classical angular frequency of the oscillator. Although arbitrarily we have chosen k by m as omega square, but still omega has the dimension of classical angular frequency of the oscillator. So therefore, omega is what we call it as classical angular frequency. We are using the word classical, it is because we are doing everything as per classical mechanics or Newtonian mechanics. So therefore, omega is what we call it as classical angular frequency. So therefore, in terms of omega square, the previous equation 2, the differential equation, can now be written as d square x divided by dt square plus omega square into x is equal to 0. So now the equation has come to a standard form, and this standard differential equation has a standard solution, has a standard. This solution admits many types of solution, but a physically feasible solution is nothing but a solution which involves either cos function or sine function. They're basically called harmonic functions, because these harmonic functions are always solutions of these kinds of differential equations. So therefore, equation 2, one of the simple solution of equation 3 can be written as x is equal to a cos of omega t plus phi. So x is the displacement, instantaneous displacement of the particle. A is the maximum value of the displacement. We call it as amplitude, and the cosine function as usual, omega t plus phi. Omega is already I have mentioned, it is nothing but the classical angular frequency. And we have some factor called phi factor. So that is called the phase factor. It is some initial phase value, or it is something like called as a phase constant. In certain situation, this may be 0, it may be some other value. So that is not a problem. Anyhow, this constant phi is what we call it as phase constant or initial phase angle. Now, so using this expression omega square by k by m, we can write the expression omega as the square root of k by m, and omega can be written as 2 pi nu naught. I have written here. So omega can be written as 2 pi nu naught. If I take 2 pi into the left side, this becomes 2 pi nu naught. So where nu naught is what we call it as a classical frequency of oscillation. There is a difference here. Omega is classical angular frequency, but this mu naught is called classical frequency of oscillation. So therefore, classical frequency of oscillation, since omega is given by 2 pi mu naught, so therefore the classical frequency of oscillation is given by mu naught divided by mu naught is equal to omega divided by 2 pi, and that is equal to 1 by 2 pi, and omega value obviously from this particular expression you can write it as square root of k by m. So therefore, classically, so the expression for the frequency of oscillation is given by mu naught is equal to 1 by 2 pi into square root of k by m, where k is force constant or elastic constant of the system, and m is mass of the particle, which is actually exhibiting so linear harmonic oscillations. So therefore, as per this particular equation, equation 5, so the classical frequency of oscillation would be decided by two factors. So one is mass of the particle, mass of the system, not rather the mass of the particle, I can use the word mass of the system, and k is the force constant or the elastic constant of the particular system. So therefore, classically, so we are able to obtain an expression for the frequency of oscillation. So for a particle which is actually undergoing linear harmonic oscillations. Please remember, so far what we are discussing, everything is based on the classical physics or the classical mechanics. We have not yet entered into quantum mechanics. We shall do it little later. Now, so we all know that when a particle actually undergoes so linear harmonic oscillations, so the particle would be possessing two types of energy. So it would be possessing kinetic energy also, it would be possessing potential energy also. So therefore, now we shall try to obtain an expression for the potential energy function. So we are calling it as potential energy function because potential energy is basically a function of the x coordinate. So the displacement of the particle, as we are discussing, one-dimensional case in which the particle is exhibiting oscillations along x-axis. So therefore, so it is simply the energy, potential energy function is simply equal to so the negative of the work done. As per work energy theorem, we can say that potential energy of the system would be always equal to negative of the work done, and that work done is actually nothing but the amount of work done needed to bring the particle from x is equal to 0 to x is equal to s. X again is the restoring force. So if the particle has to be taken from one particular position, let us say x is equal to 0, some reference position x is equal to 0, to some other arbitrary position x is equal to x, then work has to be done in order to take the particle against the restoring force. The restoring force always opposes the displacement as per Hooke's law. So therefore, if we want to take the particle from one particular position to another position, so work has to be done against the restoring force, and whatever that work done, whatever the negative of that work done, so that would be equal to the potential energy of the particle, or it's also called the potential energy function of the particle, because potential energy function is a dependent on so the position coordinate x coordinate. So therefore, potential energy function is simply equal to negative of the work done. So negative of the work done, since force, the restoring force is an example for variable force. In order to obtain the work done, we have to do the integration. So therefore, integration. So from 0 to x, from standard reference position 0 to some arbitrary position x is given by f of x into dx. So f of x is the restoring force, dx is small displacement. And we all know that from Hooke's law, f of x can be written as k into x minus k into x. So therefore, that minus gets cancelled with this one, and therefore it becomes plus. So k is constant, so therefore can be taken outside. So that can be written as 0 to x, x into dx. Integral 0 to x, x dx. And integration of x is x square. And once we substitute the limits of 0 and x, we're going to end up with the function half kx square. So equation 6. So therefore, again, according to Newtonian mechanics, so we are able to find out expression for the potential energy function of the particle. And now it is actually given by half kx square. Clearly, as per this equation, potential energy is not a constant. It clearly depends on the displacement of the particle from some reference position, let us say the equilibrium position. So therefore, if x keeps on changing, so the value of the potential energy also changes as per this particular equation. So this is what a treatment classically. So our aim is to understand the behavior of a linear harmonic oscillator quantum mechanically. In order to do this, definitely we need to apply Schrödinger's equation to this one-dimensional linear harmonic oscillator. Now this general one dimensional time independent Schrodinger's equation is now given by d square psi divided by dx square plus 2m by divided by h cross square e minus v of psi is equal to 0. This is what the equation. We derived this equation, not derive actually. We set up this equation in one of the session. So therefore, we are making use of this Schrodinger's time independent equation. So therefore, using this expression and inserting this equation 6, according to which v is equal to half kx square, we need to solve the equation. We shall try to do this one. So therefore, I am inserting this equation 6 into this Schrodinger's time independent equation. And once we insert, so then we are going to get equation in this form: d square psi divided by dx square plus 2m by h cross square into e minus half kx square of whole half psi is equal to 0. So this is what our equation 7, and therefore equation 7 is the Schrodinger's equation as applied to one-dimensional linear harmonic oscillator. Now, solving this equation is quite difficult. We're not doing it fully. We are doing it partially. Anyhow, in order to solve this equation partially or fully, so we need to introduce certain parameters to simplify this particular equation. So therefore, here we are introducing two parameters. The first parameter is y and the second parameter is alpha. So the first parameter y is linked with the independent parameter x. Basically, x and y are the same. Only thing is we are doing something like conversion. We are doing certain change of units, not change of units, it's change of scale actually. So therefore, y in terms of x is given by y is equal to 1 by h cross square root of k by k into m whole to the power of 1 by 2 into x. So this is what the parameter that we are choosing in order to simplify this equation 7. So therefore, we are going to insert this equation. Y is equal to 1 by h cross square root of k into m whole to the power of 1 by 2 times x. And this expression can also be written as k and m. So we can use expression for the classical frequency of oscillation. And once we insert the expression for the classical frequency of oscillation, this expression can also be written as y can also be written as square root of 2 pi m nu naught by h cross times x. You should bear in mind that x is outside the square root. It is not inside the square root. Where m is mass of the particle which is exhibiting linear harmonic oscillations, nu naught is the classical frequency of oscillation whose expression I mentioned previously. So therefore, y can be written either in terms of k and m in this fashion, or it can also be written in terms of the classical frequency of oscillation nu naught in this term. Anyhow, using either this one or this form, it is possible to introduce this parameter. Now, the second parameter that we are introducing in this equation in order to simplify is what we write as alpha. So this alpha parameter is given by 2e divided by h cross, where E is the energy of the simple harmonic oscillator. Please remember this one actually automatically comes from because of the Schrodinger's equation. E is the total energy of the oscillator. So therefore, the total energy of the oscillator is C. So therefore, alpha is given by 2e by h cross square root of m by k. Or in terms of the classical frequency of oscillation nu naught, alpha can also be written as 2e by h nu naught. So that is equation 8. So therefore, in order to bring this equation 7 into a standard form, which can be solved easily, we are inserting two different parameters. So one parameter is y parameter, another parameter is constant parameter is what we call it as alpha. So y, the relation between x and y is mentioned here. And alpha, the value of alpha is also mentioned here. So what we need to do is, we need to insert this y and alpha into equation 7. So inserting alpha and y into equation 7, slightly tedious, but it is easy. One can do it very easily. I have not done that one. It can be shown very easily. It is an exercise for the students. So how can we go to equation 9? So by inserting equation 8 in equation 7. Anyhow, so that mathematical thing I have avoided here. But anyhow, if we insert y and alpha into equation 7, and if we do the necessary simplification, then we are going to end up with an equation of this particular form: d square psi divided by dy square in plus alpha minus y square of psi is equal to 0. So this is what the equation that we are going to get. So after inserting the parameters y and alpha. So now this equation 9, something like, is a very standard differential equation in mathematics, as per mathematics. And the solution of this particular equation 9 is actually given in this form. So the solution of equation 9, that means the value of psi can be written in this fashion. So it is given by f of y into exponential minus y square by 2. So the standard solution of this particular equation 9 can be written in the form f of y into exponential minus y square by 2, where f of y is a function of y which has to be found out. So please remember, so our equation 9, d square psi divided by dy square plus alpha minus y square to psi is equal to 0 admits solution of this particular form, f of y into exponential minus y square by 2. F of y is something like a function which we don't know yet, and we need to find out the exact form of f of y, so which is a function of y parameter, so has to be found out or has to be calculated. So therefore what we have to do is we have to, by assuming that our equation 9 so has a standard solution of this particular form, f into exponential minus y square by 2. So what we have to do is we have to substitute this psi is equal to f of y into exponential minus y square by 2 into this particular equation 9. And after doing certain simple mathematics, it is possible to eliminate exponential minus y square by 2. So therefore we can show that. So equation 9 reduces to another standard form, d square f divided by dy square minus 2y df divided by dy plus alpha minus 1 times f is equal to 0. What we did is, so we started with equation 9. So we assumed a standard solution for equation 9 of this particular form, f of y into exponential minus y square by 2, where f of y is a function of y, unknown function of y, which we don't know, we need to find out. So therefore, after substituting this particular equation into equation 9 and simplifying, it is possible to eliminate exponential minus y square by 2. So therefore, after eliminating exponential minus y square by 2, it is possible to obtain solution of this form, equation of this form, d square f divided by dy square minus 2y df by dy plus alpha minus 1 times f is equal to 0. So therefore, we reduced equation 9. We wanted to find out the solution of equation 9, and we reduced that equation so into this particular form. So a differential equation in terms of f. And if we are able to find out solution of this particular equation, so we will be knowing f of y. And once we substitute f of y in this particular equation, f of y into exponential minus y square by 2, so we are going to get the complete solution of psi. So for equation 9. So this is what the method we are doing. Now, the standard procedure for solving the above differential equation is to assume that f of y can be expanded in a power series in y. So in order to find out the solution of this equation 10, we are assuming that f of y is something like a function of power series. It is nothing but a power series. So that means f of y can be written as a0 plus a1 into y1 plus a2 into y2 y power 2 y square plus a3 into y cube plus etc etc etc, where a0, a1, a2, a3 are some constants. We need to find them. So and here we have y to the power of 0. There is no y term here. It is all because y power comes automatically 0 here. Next we have y to the power of 1, y to the power of 2, y to the power of 3, and so on. So this whole power series in terms of summation index can be written as summation n running from 0 to infinity of an into y to the power of n. So the whole standard solution of this equation 10 can be written in this particular form. Now, so we need to differentiate equation 11. Once we differentiate this equation 11, so df by dy, so differentiation of a0 is 0. Differentiation of a1, of course a1 is constant, we have to keep a1. Differentiation of y1 is 1, so therefore it is a1 into 1. Differentiation of a2y square becomes 2a2y. Differentiation of a3y square becomes 3a3y square, and so on. So this whole expression again in terms of summation index can be written as in summation n running from 1 to infinity n an y to the power of n minus 1, that is equation 12. Now we have a term of y into df by dy. So therefore we need to multiply this equation 12 with y. Once we multiply equation 12 with y, so y into df by dy. So therefore we are going to get, I'm multiplying this equation 12 with y. So therefore I'm going to get a1 into y, 2a2 into y square, 3a3 into y cube, etc., etc., etc. And this whole series again can be done in the summation index as n running from 0 to infinity n an y to the power of n. So this is our equation 30. Now we have a term of d square f divided by dy square also. So therefore, in order to find out d square f divided by dy square, we need to differentiate this equation 12 once again with respect to y. So therefore, we are going to get d square f divided by dy square is equal to, I'm differentiating this equation. So differentiation of a1 becomes 0. Differentiation of 2a2y becomes 1 into 2a2 because differentiation of y is 1. And the differentiation of 3a3y square is, so 3a3 is constant. Differentiation of y square is 2y. So that's why I have written 2.3, not 2.3, 2.3, 2 into 3a3y3. Similarly, the next term can be written as, so 3 into 4 into a4 into y square. And this whole summation can be written again in terms of summation index as n running from 2 to infinity n into n minus 1 n y to the power of n minus 2. Here we are starting with n is equal to 2, but we need to change from n is equal to 0. And if we do this change, rather than starting from n is equal to 2 term, if we start from n is equal to 0 term, then this whole equation can be written as n plus 2 into n plus 1 a of n plus 2 y to the power of n. So this is what equation 14. Anyhow, so from here I need to continue. So I'm taking a break here. I want to continue in the next session. So we will continue our discussion in the next session starting from this equation 14. So thank you all.